In this section, we'll talk about the boosting idea. Boosting is a special machine learning technique that uses several weak learners to produce a stronger model at the end. It is also something quite different when it comes to the bias variance trade-off. So far in this class, we saw that if we aggregate some random multiple models, we usually reduce the variance with some small trade-off in bias. When it comes to boosting, it's quite different because we are using some weak learners, so they will have some high bias. This time we will try to aggregate models to reduce bias without introducing too much variance. Before we dive into the details of this algorithm, let's actually take a step back and think about a simple problem. Assume that we are given a regression problem with this data set xi, yi, and we want to produce a model f of x that minimizes some mean squared error. So here's our loss function for that. In this loss function, you will see this 1 over 2n instead of 1 over n. So that's something I will explain later, but you can simply assume that this is a simple loss function for the mean squared error. Let's continue with our assumptions. Let's also assume that we have this model f sub 0 given to us as a trained model on this data set. And they ask us to improve this f sub 0. So we want to make this f sub 0 better. What can we do about this? An intuitive way to improve this model is to look at the errors. Because if we can understand what type of errors are coming from this model, maybe we can improve the model. So let's do that. Here we can calculate the errors like this. We have the labels, we have the predictions. Here's the error. Then in the machine learning world, if we try to understand something, we sometimes fit a model on that. So let's do that. This time we will fit the model called g sub 0 on this error, and we will try to understand that. Here's our loss function. And more intuitively, this g sub 0 is trying to approximate the errors. Then we will add them up. Here's our original model plus g sub 0. And that becomes a new model f1 of x. And overall, this is the boosting equation. Let's try to explain this summation here. Why we add them up. In order to explain this, I'm just using a numerical example here. Let's assume that I have this -3 error here at this specific data point I. If this is -3, it means that my model is producing something larger than the label. And as I am fitting this g sub 0 on this error, it is trying to approximate this -3 here. When I add them up, this f sub 0 is producing something large, and this g sub 0 is trying to bring it down. And if it can bring it down, it means that the error will also go down. So that's the idea behind the boosting technique. We will have these models, then we will calculate the residuals, then we will fit another model on these residuals. And overall, this process will reduce our total error. Let's explain this in an algorithm. We are not just limited to a single g sub 0 here. We can have multiple of those, and we can have a large aggregate model. Let's start with our model f sub k, calculate the residuals, fit a model on this, add them up, have a new model, go back, calculate the residuals, fit another model on the residuals, add it up, and overall get a larger aggregate model. So that's the idea behind the boosting technique. And in theory, we can start with any model, so our f sub 0 can be something simple, just like the average value. But as long as our model's g sub k's can do better than guessing the average value in our data set, we will continue to improve on our cost functions. So that was the idea behind boosting. Let's also talk about these weak learners and what do we really mean by improving. In this technique, we prefer using weak learners for a reason, because we don't want these g sub k's to learn these errors very quickly, because if that happens, that usually leads to overfitting in early stages. And for that reason, we will use weak learners. For regression, weak learners means that some type of models that can reduce the mean squared error compared to the guessing the average value. So they do better than guessing the average value. Also for classification, again, those are going to be models that do better than random guessing the class. So I explained this in simple words, but the concept is quite technical actually. So you can take a look at this blog post for more details about that. A good example for a weak learner is a short decision tree, for example, a tree with less than 10 nodes, or even a decision stump, which is made of a single node. But in the real world, usually decision stumps do not work that well because we usually deal with some complex problems. But overall, this weak learner idea is important. We will always have these weak learners. And as they are weak learners, they tend to have some high bias with them. And that's pretty much the idea behind the boosting and the weak learner. Next, we will see a notebook example. And here's our exercise from this notebook. In this exercise, we will use a boosting method with different numbers of weak learners. And we are also using decision stumps as our weak learners. Let's first create our data set. Here we have a regression data set. Our x1 and x2 features are sampled from a normal distribution, and y is the square summation of these features. And the data set looks like this. First, we have a boosting method with a single decision stump. Here, this single decision stump will only have a single split as expected. So it is this point, and beyond this is this large value, and before this is this smaller value. Let's jump to two stumps. This time the first stump will fit on the data set, then we will calculate the residuals, then the second stump will fit on these residuals, and overall we will have this surface here. Let's increase the number of stumps, and this time we will see that we will have some more complex surfaces. For example, 4 stumps look like this, so we have these 4 corners for these data points, and as we increase it even further, we will have even more complex surfaces. For example, 16 looks like this, 32 looks like this, and overall 64 looks like this. And as you see, as we increase the number of weak learners, we will tend to approximate this data set even closer. If you want to experiment with different parameters, you can follow this notebook here.